In today's lesson, we are going to be looking at organized counting and the fundamental counting principle. So this is going to kind of build off of kind of what we've looked at in the last unit in terms of probabilities, but we're going to be looking at different scenarios, more specific scenarios that kind of have unique characteristics. Before we get into that, let's kind of review what we've learned already. So our sock drawer, or your sock drawer, has 18 folded pairs of socks with 8 pairs of white, 6 pairs of black, and 4 pairs of blue. What is the probability, without looking in the drawer, that you will first select and remove a black pair, then select either a blue or a white pair? So again, I'm just going to recommend that you pause the video to try these questions, just to kind of review what we've learned so far. So again, this one had two kind of complicated parts. One, we had to keep in mind that we were looking at two dependent events because we were removing a pair, and because it was one event followed by another, so we have to multiply. And selecting either a blue or a white pair, those were mutually exclusive, because two different events, they wouldn't exist at the same time, so we would just add them together. So kind of combined both independent and dependent, and mutually exclusive and non-mutually exclusive. So for a black pair, 6 out of 18 multiplied by 12 over 17 for 12 blue or white options, and then we divide by 17 because there's one less, or with that black pair being removed. We should get 23.5%. One, a study found that 81% of households in the United States have computers. Of those 81%, 92% of them have internet access. Find the probability that a US household selected at random has a computer and has internet access. So again, pause the video, try to do this question on your own. So this is an example of a dependent event or conditional probability. The probability of having a computer is 81% multiplied by the probability of having internet access given that you have a computer is 92%. So 81% times 92% gives us 74.52% chance of selecting a household that has a computer and internet access. A doctor gives a patient a 60% chance of surviving bypass surgery after a heart attack. If the patient survives the surgery, he has a 50% chance that the heart damage will heal. Find the probability that the patient survives and the heart damage heals. So again, similar to the last one, so I recommend again pausing the video and trying this question on your own to review. So again, this is another example of a conditional probability. The probability of the patient surviving multiplied by the probability that the heart damage heals, given that they survive, is 60% times 50%. We get 30% chance of them surviving and having the damage healed. In a sample of 1,000 people, 130 can wiggle their ears. 2 unrelated people are selected at random without replacement. A, find the probability that both people can wiggle their ears. B, find the probability that neither person can wiggle his or her ears, or their ears. Or C, find the probability that at least one of the two people can wiggle their ears. So again, 3 different questions. Again, pause the video, try to do these on your own as a review. Coming back, these are examples of conditional probability again. A little bit different because we have to calculate the different probabilities. They're not given to us. So we do have to keep in mind that the second probability will be changed, or will have changed depending on what happened in the first event. Because they are followed one after another, they are dependent, we are multiplying. So the probability of both people wiggling their ears, 130 over 1,000 times 129 over 999, because there is one less person that can wiggle their ears, assuming that we picked them in the first round. And then there is one less person overall because we took one person out of the total group or the sample. So we end up with 1.68% chance of that happening. Probability for neither person wiggling their ears is same idea, except we're using 870, which is the amount of people that can't wiggle their ears, divided by 1,000, multiplied by 169, because we took one of them out in the first round, divided by 999, because there is one less person from the sample. We get 75.68%. For C, find the probability that at least one person of the two can wiggle their ears. So I've chosen to do the indirect method. So rather than looking at all the possible outcomes of selecting at least one person that can wiggle their ears, I decided to do the indirect method, which is think of the opposite or the complement to at least one person being able to wiggle their ears. So at least one of two means one person, whether they're selected first or second, or two people that can wiggle their ears. So you'd have to add up those three scenarios. First person being picked that can wiggle, and the second person can't. Then the next scenario, the first person can't wiggle, and the second person can. And the last scenario, both people can wiggle their ears. So you have three different scenarios to add up. Again, like I said, I chose to go the other way, where I subtract the opposite or the complement to that, which is that none of them can wiggle, which I already had the answer for in part B. So that's why I went that way. Is a little bit easier, less work to do. So 1 minus the probability that that neither people can wiggle their ears, we end up with 24.32%. So there's a 24.32% chance of selecting at least one person that can wiggle their ears. So we are going to be moving into a new unit, and we're still going to be dealing with probability in the end of it. We're going to just be looking at different ways now essentially to count things, or different ways we can do things. So the first thing we're going to look at is the fundamental counting principle. A couple things we want to remember. And means multiply. Right? So referring back, and means multiply. We've talked about that before, looking at one event and another. So we can kind of continue to take that from probability and put it into just counting. So if there are m ways to do the first event, and n ways to do the second, and so on and so on and so on, the total number of ways that two events can be performed is just m times n, just multiplying those two events or numbers together. And this is not limited to two actions. We could have 3 events, 4 events, 5 events. It would be the same thing, m times n times o times p if we want to keep it alphabetical. The number of ways to do the first times the number of ways to do the second times the number of ways to do the third times the number of ways to do the fourth event. And again, not limited to 4, it could be more than 4 possible actions or events. So let's take a look at that. A school uniform consists of a shirt, pants, and shoes. Students can choose between white or red tops, black or navy pants, and black or gray shoes. And how many ways can a student get dressed in the morning? So we've done this using a tree diagram in the past. So let's look at that. We're going to start with our first option. This would be our shirt. So just kind of reviewing. So make sure if you're putting titles in your tree diagram, put them above the branches. You're not going to have them be a part of it. Right? So the first one is shirt. We have white or red. And then off of there, we have different pants. So we have black or navy. And the same thing off of the red tops, black or navy. And then off of each of those, we have our shoes, which are either black or gray. And this is off of each option, black or gray, black or gray, black or gray. So how many ways can they get dressed in the morning? Well, again, one of 2 ways. You can go through and count each pathway starting from the beginning, right? So the example, this would be, this would be one pathway. White top, black pants, black shoes. That's one pathway. You You could do white top, black pants, gray shoes. That's another pathway. Another thing you can do is just add up the number of options in the last column. So blue gray, 1, 2, 3, or black gray, 1, 2, 1, 2, or 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 total ways to get dressed in the morning. If we wanted to use the counting principle, what that says is the number of ways we can do the first event. So for shirts, we have 2 shirts or 2 tops, multiplied by the number of ways for the second event, 2 pants, multiplied by the third way, which is 2 different pairs of shoes. 2 times 2 times 2 equals 8 total ways. Now, the one downfall to the counting principle is that it doesn't tell you the number of outcomes. All it does, it does tell you the number of outcomes. It doesn't tell you what each outcome is. So that is the one benefit to the tree diagram. We do get to see what each individual outcome is. When we're using the counting principle, we only know the total number of ways, right? We don't know what each individual way looks like. So there are benefits to them. So example 2, you roll a standard die. How many outcomes are possible with 2 rolls and 3 rolls? Well, our first roll and our second roll, how many outcomes do we have in our first roll? We have 6 possible numbers multiplied by 6 possible numbers for our second roll, which gives us 36 outcomes. Again, remember, it doesn't tell us what the specific outcomes are. It just tells us how many we have. For 3 rolls, same idea. 6 for the first roll, 6 for the second. The third roll doesn't change. So 6 for the third roll, so 36 times 6, 216 outcomes. Next example. There are 20 students in a classroom. In how many ways can we select a president, vice president, and treasurer if A, there are no restrictions? So this one's going to be a little bit different. So if I look at picking the president, the vice president, and the treasurer, I have to think, well, of the 20 students, how many people could be picked to be the president? Well, in this case, there are 20. One of them gets picked for president. How many options do we have for vice president? We have 19 now. And then what about treasurer? 18, assuming that one got picked for the vice president. So then in total, 20 times 19 times 18, we get 6,840 ways that we could select these 3 positions. What if there are only 3 students who are eligible to become president? How does that change things? Well, let's go take a look. We have our 3 events. If I look at the first event, the probability of becoming a president, there are only 3 students that are able to become that. Does that change the next one? It doesn't, because we still assume there are 20 students in total. One of them gets picked to be president. Those 2 people that didn't get picked go back into the overall group. There's still 19 and then 18 possible people for the other 2 positions. So 1,026 ways that we could select these 3 positions if only 3 students can become president. Is Mike, followed by Julie, followed by David, different from selecting Julie, followed by David, followed by Mike? So take a second to think of this. Is selecting Mike, followed by Julie, followed by David, different from selecting Julie, followed by David, followed by Mike? Now you might think, well, there's only one way this can happen, which is true. right? Because if we think of there's only one Mike multiplied by one Julie multiplied by one David for president, vice president, treasurer, there's only one way. And if we do it the other way, it's the same thing, right? So if this was Mike, Julie, David, Mike, there's still only one way to do that because there's only one of each person. But are they different? And in this case, yes, they are different. So even though there's only one way that these outcomes can occur, they are different. And the reason is because we have different positions. Right? So they are different, even though there's only one outcome, because you're looking at Julie being president, David being vice president, Mike being treasurer. That's different with Mike was president, Julie was vice president, David was treasurer. So yes, they are different. You could say different orders / positions. So they would be in different positions, meaning that they are different. They have different roles. So it's different, even though there's the same possible ways that it can occur. Example 4, the following lock that we can kind of see off to the side uses 5 slots and a letter for each slot. How many ways are there to have a password with no restrictions? Well, no restrictions. So in this case, no restrictions. Let's look. We think of our 5 different possible events. And this kind of method is called the slot method because you're basically putting down different slots or different spaces for the different events that can occur. So it's an easy way to kind of visualize and think about the event, right? So you have your first number, your second number, your third number or letter, your fourth letter, and your fifth letter. If there are no restrictions, well, how many letters are there? 26 letters. So 26 letters, so 26 possible options for the first one. And just for honesty, I did have to Google that. I paused the video for a second just to double check because it's one of those things that you're maybe never quite sure because you don't get asked that a lot. But 26 letters. And if there's no restrictions, you can use 26 possible letters for the second, 26 letters for the third, 26 letters for the fourth, 26 letters for the fifth. So if there's no restrictions, I can use the same letters each time. It could be A. Not the best password, but it's a possible option. So in this case, 26 to the power of 6, or 26 times itself 5 times, or 26 to the power of 5, sorry, or 26 times itself 5 times, 11881376. So 11,881,376 possible ways or outcomes for this 5-letter password. Now B, you can only use each letter once. So in this case, again, I'm going to go back to the slot method, looking at each possible event. In this case, the 5 different letters. Now, because I can only use each letter once, the first option, still 26. Second option, there's now 25, because whatever letter I picked in the first event, I can't pick it in the second. So that means there's only 25 options remaining. Then 24, then 23, and then 22. 26 times 25 times 24 times 23 times 22. 7893600. So 7,893,600 letter or possible outcomes if I cannot repeat letters. Lastly, the password does not, or not lastly, second lastly, the password does not contain vowels. So for our argument A, E, I, O, U, in any question, I would assume that those are the 5 vowels we're using. We're not going to do the sometimes Y. So A, E, I, O, and U. So we're not using those letters in our password. So again, I'm going to go back to the 5 possible events or 5 slots for our password. Now, if I don't have any vowels, A, E, I, O, U, that means that I have 21 possible outcomes. Now, the next part may depend on other specifics, right? We need to know, are we allowing repeats or are we not allowing repeats? Well, let's just do it both ways. So in this case, I'm going to use no repeats for this one, just because repeats are a little bit easier. So no repeats, so 21 options, then 20, then 19, then 18, then 17. Because one letter gets taken, leaves me with one less for the next event, and so on. So 2441880, 2,441,880 outcomes when we're dealing with no repeats. And if I look at no restrictions or repeats allowed, so allowing repeats, 21 to the power of 5, or 21 times 21 times 21 times 21, and so on. So 21 to the power of 5, in this case, 4084101. So 4,084,101 outcomes. So you can see how it changes. Obviously, having more outcomes or more possibilities for each event allows for more outcomes. What is the probability of correctly guessing the code if you randomly select letters? So this one might be a different, a little bit more difficult. We have to think about NA and NS. Total number of successful outcomes, or a total number of possible outcomes, in this case, getting the answer. And NS is the total number of ways. So let's think of them separately. How many correct codes would there be? How many possible options are there for getting the right code? We don't know what the code is, but if you think of a lock, there can only be one code. So the probability is going to be 1 over, now, the total number of ways. How many possible ways are there to have a code? Now, for this one, let's go back up to the total number of outcomes, thinking about how many possible ways there are. So the 11881376. 11881376. So it is a 1 out of 11,881,376 chance, or if we determine the probability of this as a decimal, we get, we'll turn it into a percent. So we have 8.42 times 10 to the negative 6% chance of this occurring, or basically 1, 2, 3, 4, 5, 6, 842%. So 0.0000842% chance of this occurring, and you can see that's a very, very low percent of correctly guessing the code. But the reason we have, or the reason now, if you look at entering a password, it's not just letters, it's numbers, it's characters, right? It's uppercase, lowercase. It changes. There's more and more options that they're allowing or requiring you to have in your password, because it creates so many more possible outcomes. And the idea is that if you only allowed, say, a password containing no vowels and no repeats, you only have 2 million, roughly 2.5 million possible outcomes. Now, as a human or yourself, trying to guess what that password could be would be very difficult. However, if you're doing it, if you have a computer that will randomly generate and enter the different passwords, that's a different story. A computer could probably come up with those outcomes relatively quick, depending on the program or the computer. So that's why you have to, passwords now tend to require more and more passwords, or more and more characters in the password to make it harder for computers to guess, or to make it the number of outcomes so vast that it's difficult for a computer to generate and test all of them. So just kind of a little tidbit there. So homework. So there are kind of two sets of homework. You can take a look at them. We do have a couple practice periods, or just for extra practice. But again, this is just kind of looking at different ways to kind of count things rather than having to create a tree diagram, because looking at some of the scenarios, it would be a little bit too difficult to do that.